please start? Thank you.
Yep, ready we are. Good afternoon, everyone. Today, my group and I are going to show you our progress on making multimodal large language models understand charts better. Multimodal large language models, or MLLMs for short, you might be asking yourself, oh, hold on. You might be asking yourself, if we move to the next slide, please. You might be asking yourself, why is it? Yeah, what is an MLLM? If we move to the next step, you're going to realize that, well, take a look at ChatGPT. Do you see that little attach images thing that's there? That's pretty much it. You take an image, you put your text prompt, and you get a text result out of it. Now, moving on, we're going to ask ourselves, what are we doing exactly? Well, what we're trying to do is, if you give a chart and you put it with text to an MLLM, it's going to get mad confused. So how do we circumvent this issue? Well, that's pretty much our entire point. We're trying to make it do better. We're trying to make it understand things better. So if we move on, we're going to explain why are we doing this in the first place. Well, next up, we know that over 50% of data scientists' time is spent pretty much just on pre-processing, but there are existing tools that help with that. In contrast, there aren't nearly as many tools that help with the menial conclusions that prevent a data scientist from sinking their teeth into the juicy meat and potatoes of it all. So AI can be a useful tool for research. Now, moving on, we're going to ask ourselves, why are we considering MLLMs in particular? Well, let's look at the following. MLLMs are a rapidly developing field. On top of that, they are very good at processing text. However, they are not really that good at processing chart and structured data. So there's a lot of room for development. What do I mean? Well, let's look at the next example. As you can see here, the question says, how tall is the tree after 9 years? The answer, obviously, 80 inches. When we asked DeepSeek and ChatGPT-4, their answers were 90. Quite a bit off the mark there. The closest one was 01, and it got 82. So the workhorses that took us throughout this entire journey are two devices that are both kitted with an RTX 3090 with 24 gigabytes of VRAM. They also have 64 gigabytes of RAM each, and both have a Core i9. Now, onto our progress with my colleague, Carolus.
Starting with a quote by Thomas Edison, I have not failed, I've just found 10,000 ways that don't work. We have gone a long way before we touched on our champion model. Starting by our very starting point, the datasets. We relied on three main datasets, ChartQA, MathVerse, and Chart-to-Text Stat System. Together, these datasets provide a high quality, human annotated, multilingual, multimodal questions and textual and pictures questions. We have done a lot of experiments. These are the experiments that we have done practically and ran on our machines. On the left are LLMs, large language models, and on the right are the vision encoders. You can find in bold the ones that are the highlights of our thesis project. We started by some fine-tuning, and these are the results of the fine-tuning. We fine-tuned Quen and the 5.4 Mini. But results of the fine-tuning weren't very promising. So we started by investigating some techniques, starting by prompt engineering. And by prompt engineering, we do start by some question classification. Either the question is a fact-based, numerical, or reasoning question, and then selecting a prompt based on that, and then guiding the model to use this prompt, and finally extracting the data and values from the answer the model provided. We also used quantization using QLoRa because we couldn't run most of the models of the big models on our machines because of limited memory challenges. We did the quantization. We converted the model weights to 4-bit precision using bits and bytes. And we froze the model weights and only trained the adapters. We also tried investigating and experimenting with a custom architecture of our very own. We tried different vision encoders, and we finally chose Dino V2. We trained the projector. Next slide. We first tested, and it didn't provide like promising results also. And then we did some fine-tuning on the projector. Next. We trained the projector on the ChartQA dataset, and we also trained it on the chart-to-text dataset. And then we redid the tests, but also the model still got some questions wrong. So we started investigating a new approach, a new model, a new architecture, and that was our very first touch with our champion model. And now I'll leave my colleagues to present about how we did achieve an outstanding accuracy, outperforming a lot of models, introducing my colleague, Raghav.
Okay, now I will be presenting our table-first guarded reasoning pipeline. It's a simple yet powerful pipeline designed for chart questioning answering tasks like chart QA and plot QA. As you can see here in this pipeline, we start with the chart and try to convert it into structured data using one of the models that converts chart into structured data like dplot. dplot is a model built by Google and has been trained and pre-trained on very big corpus of data to transform a chart into structured data. Then we pass the question alongside with the structured data to the text-to-text model, which is Qwen 2.5, 3 billion parameter to get an answer. And now let me walk you through our pipeline using an example from a ChartQA dataset. Given this chart in the left and the question, what is the average of yes category from 2010 to 2017? As you can see, the pipeline extracted the data precisely, and the text-to-text model started by summing the values in yes category and then divided them by the number of elements, which is true logic, but it failed miserably in math. Therefore, we ended up getting 21% accuracy on a ChartQA dataset, which shows that our model still struggles in math and reasoning. So, to resolve these issues, we've implemented chain of thoughts reasoning steps and integrated external solver, trying to mitigate and handle the math and reasoning issues. So now, after implementing different chain of thoughts reasoning steps and using external calculator, the pipeline now made the best use of the calculator and used it to calculate the sum of the yes category. Then, in the second step, use the same external calculator to divide this number by 4 to obtain the correct answer. Therefore, our initial table-first guarded reasoning pipeline enhances the performance from 21% to 40%, getting 19% absolute gain. And now my colleague Andrew will talk about the further changes that we made on the pipeline that made us outperform the state-of-the-art models.
Okay, so as we saw, using a Qwen 3 billion parameter model with dplot nearly doubles our accuracy. However, to bridge the gap to the state-of-the-art performance, we needed to implement some major changes. So firstly, we decided to scale up the reasoning model from Qwen 3 billion parameter text-only model to Qwen 7 billion multimodal model to handle more complex reasoning and mathematical tasks, and to enable a dual modality approach because we switched it to a multimodal architecture. So now we can send the image, the chart image, to both the extractor and directly into Qwen's vision encoder to ensure that the model has the complete information. So the table provides the exact numerical precision, while the image preserves the global context. And secondly, we removed the intermediate solver, and we will see why in a while. Also, we tried a different extractor other than dplot, which is a chart-to-table model. So this model is 2 times larger than dplot at 0.6 billion parameters, and also more robust at extracting data from complex layouts. So to show that this complex architecture was necessary, we decomposed the performance to see exactly how much accuracy each component contributed. So firstly, we tried just using the baseline model, which is Qwen 7 billion multimodal model alone, and this resulted in an accuracy of 88% on a chart QA test dataset. Then we kept the same model, but applied our chain of thought prompting. So we forced the model to explicitly extract the relevant data points from the chart images and to also drive the answer step by step. So this improved the accuracy from the baseline by 2.8%, reaching a total accuracy of 90.8%. So to visualize exactly how this improvement happens, we firstly give the baseline model this chart image along with this question, which is the value of the light green bar 35 in 1989? And the ground truth was yes. So the baseline model incorrectly predicted no. However, when we tried the baseline with the chain of thought, the model was forced to perform an intermediate retrieval step and explicitly extracted the relevant data for the year 1989, which allows the model to see the correct number and correctly answer yes. Then we integrated the external extractor dplot with the baseline and the chain of thought to generate a table and fed it to the Quinn model alongside the image. So this also improved the accuracy by 1.7%, reaching a total accuracy of 92.5%. And finally, we tried the chart-to-table extractor because of its superior ability to handle more complex structures compared to the dplot extractor. And we reached our peak performance with an accuracy of 93.9%. So to show how the table extractor actually improves the accuracy, we firstly tested the baseline model with this chart image along with the question, which is what was the largest dark red bar value, and the ground truth was 0.08. So the baseline model incorrectly predicted 0.26. Also, when we tried the baseline with the chain of thought, it doesn't answer correctly because it couldn't extract the red bar values from the chart image. However, when we combined the baseline with the chain of thought and the chart-to-table extractor, the model looked at the extracted table and saw the precise values for the dark red bar in the chart image and easily identified the correct answer. And now my colleague Magd will continue with the results.
So let us look at the exact fruits of our labor. On your left, right here, you're going to see something called the Chart QA test leaderboard. What it does is that the different MLLMs compete head-to-head to see who can perform best in Chart QA's charts and question pairs. The current state-of-the-art, or previous more accurately, is Qwen2 VL 72 billion parameters. I'll explain why that's a big deal later on. It got 88.2% accuracy. Meanwhile, our baseline got 88% accuracy. Add a little bit of salt and pepper with chain of thought, and you get 90% accuracy approximately. Add a little bit of spice with the dplot, and you go all the way up to 92.8. And a little bit more, and replace dplot with chart to table, and you go all the way up to 93.94%. Why is that a big deal, though? Well, for starters, this is a bit of a David versus Goliath situation. We have a model that is at most around 8.5 billion parameters, beating out a model that is 72 billion parameters. This massive difference in size makes it so that our approach can be run on significantly weaker devices, and also allows us to use less energy and less resources, which can act as a starting point for more eco-friendly AI. But you might be asking yourself, if we move on to the next slide, why did we end up removing the solver to begin with? Didn't it make improvements? Well, in the smaller system, it did. But here, when we upgraded to Qwen 2.5 VL 7 billion, what happened is that the model's own solving capabilities became better, therefore making the solver redundant. On top of that, the act of delegating simpler tasks to the solver increases the overhead unnecessarily. And on top of that, sometimes the solver is used without an actual reason, like using it for counting when it could have just relied on the visual aspect. So in the end, on top of all of that, you need to learn when to use the solver, which hurts the ability to use the LLM whenever you just want to give it an image and text and get it over with and get an answer. Now, I'm going to let my colleague Sheza explain exactly how we measured our results.
To produce all these results that Mag just said, we use a chart QA dataset to test our pipeline. We used it because it fully represents the charts domain by including noisy charts, unconventional layouts, and logically challenging questions. The chart QA dataset is composed of 2,500 samples divided into 1,250 samples human-generated and 1,250 samples machine-generated. The machine-generated ones are used for testing our pipeline abilities on synthetic visuals and just the raw data extraction, while the human set, the more challenging ones, are used to test our pipeline abilities on deep reasoning and complex annotations. And to do the evaluation, we use the official evaluation function used on the chart QA leaderboard that we have just shown. This function mainly works by normalizing both the ground truth and the pipeline answer, and then do substring match for text formatted answer, but for the numerical answers, we use 5% tolerance margin to compare the pipeline answer and the ground truth. The normalizing function works mainly by lower casing and removing the punctuation of the answer and removing all the signs of currency, percentage, blank spaces. And we also extract the digits from the answer, or if there is a word that signify a number, we convert this word to digit so that we can use it in comparison with the ground truth. For example, the LLM might output the average revenue is about $5 million, while what we want to compare with the ground truth is only the $5 million digits figure. So that is why this function is essential, so that we're not penalizing the model and the whole pipeline for being polite or communicative. And for the full processing steps, the pipeline takes the query and the image as input, and it goes through the full pipeline that we have just explained. And it outputs the answer in chain of thought formatted answer. But we need to extract the final answer that we do by parsing the full answer, searching for the keyword final answer. We extract this part, and then we normalize as we just explained, and do the scoring using the 5% tolerance margin or substring match. And all of this will be shown in action with my colleague Tara in demo application.
Okay, we did a demo application so that we can compare our pipeline with the base model and see the improvement. So as you can see, okay, so as you can see, you write the question and attach a chart and send it to both of these models who are running locally in our campus, and then you receive the results. As you can see, the older model produced a wrong result, which is 28%, while our model produced the correct result, which is 8. As for the empowerment outcomes of this project, it was very empowering. We proved that we can compete against state-of-the-art and push it further and develop it further. We produced a research paper and are going to submit it to the IEEE Conference of Artificial Intelligence this year. And we have made a demo application so that anyone on campus can connect to the servers and test out our program.
To conclude, I'm glad to highlight that we achieved 93.96 accuracy on the chart QA dataset and evaluation. We did that using a 7 billion parameter model, outperforming even bigger models and even the state-of-the-art. I would like you to think of that. We have made chart analysis and reasoning far more accessible to many more researchers and organizations. Thank you.